Hello, welcome to Keeping Your Cool, Thermal Considerations for TI Analog Products. This is part 4 of our 4-part series, and this is entitled The System. I'm Matt Romig from TI's Analog Packaging. In this 4-part series, we've looked through 4 common thermal questions that we get and interact with our customers about. We've looked at the basics, we've looked at the temperature, and we've looked at the device itself, and in this last section, we will talk about the system, looking at the impact of PCB layout, system design, those type of things on thermal performance, and hopefully give a little better understanding as well as some recommendations. Congratulations for making it this far. So the first point to mention and talk about from a system perspective is we're oftentimes looking at just one component. We're looking at a certain power management component or processor or whatever. But the other components do matter very much to the thermal performance of the component that we're looking at. So we'll look at 2 examples here that illustrate that. This first example is a model of a telecom rack looking at an array of devices, similar devices over here on the left and then some other devices here on the right. And this is a modeling exercise that's set up at 50 degrees C ambient with 300 feet per minute of airflow. So what we see here is when we look at 20 devices, so when we look at this array on the left, if there are 20 devices in this array and each device is at 3 watts, then the junction temperature of the hottest device is 106 C. And if we calculate an effective theta JA by taking the junction minus the ambient divided by the power, we get an effective theta JA in that configuration of 19 degrees C per watt. Now if we take the same setup, but we eliminate half of the devices, so we make it 10 devices at 6 watts each, we get a similar junction temperature, a little bit hotter at 109 C, giving us an effective theta JA for each device of 10 degrees C per watt. So what does that mean? The effective theta JA, if we look at each component, doubles when the density of the components around it doubles. And more specifically, that means that the theta JA of each component is highly dependent on the components around it. It is not just a function of the component itself. Here's another example of looking at a model of a set-top box. So this is a case where we're looking at this device here in the middle, and this is a device that runs at 1.4 watts, and the set-top box is assumed to have a 50 degrees C external ambient. When the device itself runs, we measure 85 C. When we turn on the hard disk drive next to it, the temperature of this device goes up to 107 degrees C, or a 63% increase in the effective theta JA. And when we tune on the hard disk drive and the tuners down here, the temperature of this device in the middle goes up to 126 degrees C, or over 100% increase in the effective theta JA. So what does this example show us? It shows us that when we turn on other components, the effective theta JA, again, can increase significantly and can more than double. Whether they're similar components in the first example or dissimilar components, really any heat source inside the system can affect the temperature rise of a particular component that we're looking at. The next example to look at is the PCB itself. The board construction does matter to the performance of the part. So this is a modeling exercise looking at a single part which is dissipating 6 watts on a PCB, and you'll see the data over here shows that when we look at a JEDEC defined board in terms of layer thicknesses, stack up, those kind of things, we get an effective theta JA of 29 degrees C per watt. When we look at an EVM or a power board that's designed around this actual device, in a 2-layer board, we get an effective theta JA of 25 degrees C per watt. And when we look at a 4-layer board, it goes down to 18 degrees C per watt. And the point of this slide is not to give specific numbers that talk about JEDEC boards versus EBMs or rules of thumb comparing 2-layer versus 4-layer, because those can be very board specific or device specific, but really just to illustrate the point that the effective performance, thermal performance of a particular component can be significantly affected by the PCB construction itself. The next example to look at, and looking a little bit more specifically at PCB layout, are concepts of thermal footprint and thermal coupling. So the first one is what we'll call thermal footprint. And a thermal footprint refers to the area on the PCB around the component of interest that participates strongly in the convection or radiation, or similarly, that is noticeably heated up by that device when it's operating. modeling and analysis has shown that this area is about 18x the package area, or about 2x in the x and y direction, and if you add all that up, it comes out to about 18x the total area. So you can see a little illustration here where here's the device that's heated up, and a rough view of what 18x or what a thermal footprint looks like around that device. Then what that leads to is the concept called thermal coupling. When you have multiple devices on a PCB that are dissipating heat, they are thermally coupled, or they interact with each other. And particularly, anytime their thermal footprints overlap, you essentially get, referring back to part 3, you essentially get saturation, thermal saturation, where the effectiveness of the convection and radiation in that area of the board goes down because it's saturated, or the effective cooling of each of those parts goes down. And really the point to illustrate, and I'll show this in the next slide, is that when the thermal footprints overlap, it can significantly affect the junction temperature of each of those components. So here's a specific example where we look at 4 different devices, and in our baseline case, we have these relatively small components separated by 50 millimeters. So you can see their thermal footprints have very little overlap. You can see the blue very slightly overlaps, but the other colors illustrating where there's really noticeable heating up are pretty far from each other. So let's see what happens as we move those closer together. We go from a max temperature on each of these components, because these are the same, so they all have the same temperature. It's going to go from 81.6 to, when we move them to a separation of 25, then the max temperature goes up a little bit to 84.4. When we then move them closer to 12.5 millimeters apart, we've taken a significant step up to 92.9. And when we move them closer still down to 8 millimeters, we've increased the temperature of each of those devices up to 98.4 degrees C. So this is a specific example that illustrates very practically or very quantitatively what happens when we move devices closer together and account for the overlap of their thermal footprints. So obviously, as components and systems miniaturize, this is a reality, and this is something we have to be aware of and design around. So in the next slides, I'll go through a little bit of some factors to consider and some design best practices. So here are some factors to consider. Clearly, as we looked at, the layout of the PCB matters. And so as you're looking at system layout, you need to think about component layout, and particularly those components that are dissipating relatively high levels of heat, and looking at the power density hotspots or localization on the PCB to try and minimize the footprint overlap or the coupling as much as possible. Secondly, looking at airflow effects. So this is both globally, the entire system, and locally around the parts. And this is not just referring to situations where we have a fan, because many systems don't have the luxury of having a fan for cost reasons or for system size reasons, but also the effects of natural convection within the enclosure. The PCB may cool differently in different locations, and so oftentimes looking at how the air moves in different locations can help. And particularly with heat sinks, heat sink vendors publish values, and those are very helpful as a starting point, as references. But oftentimes the performance of a heat sink will be different in a real system than what was measured by the vendor in the wind tunnel where they took the measurements. So it can be helpful to look at the airflow effects both globally and locally. More specifically on natural convection, the enclosure design greatly affects the natural convection. So one rule of thumb is that natural convection needs a space of about 6 millimeters or more to be able to move freely and to be able to behave as convection and not just as air conduction. So looking at spacing above components, spacing between PCBs and chassis, venting can be very important, and designing vents to enable good natural convection effects as well as to cool the particularly hot components, as well as looking at, in the enclosure design, where is there plastic and where is there metal. Where there's plastic, it generally restricts any conduction or any heat flow. Where there's metal, it can oftentimes help. The chassis can help to spread out the heat and make the convection more effective as well. And lastly, looking at air temperature variations inside and outside the enclosure and at different locations within the enclosure. So looking a little bit deeper than assumptions like, well, the air temperature outside is 85 degrees or 70 degrees or 50 degrees, or the temperature inside the enclosure is a certain temperature. But looking within the enclosure, where is it heating up? how is the air moving around, and how do we encourage mixing of air, and how do we encourage heat spreading, and ultimately improving the thermal performance of the system. Here are a few examples of some best practices. I won't walk through every single one of these, but I will illustrate a few of these and talk through them a little bit. So one to talk through is specifically in PCB layout, and this illustrates concepts of not breaking the heat flow through the planes or putting PCB vias under or near the device. So in this example, the component of interest is in purple, or is kind of framed in purple and pointed to in green. The concept of heat flow, so if you look at the red arrows, the heat is flowing from the thermal pad here down out into this plane here, as well as up into this plane here. And the best practice in this example, and it's illustrated particularly well down here, is to avoid breaks in the plane, which would break up this kind of this highway or this channel that I'm illustrating here with the mouse, where the heat can flow through a wide area to get to a large plane, which can then provide a good surface area for convection or radiation. Another example here, you can see these little silver dots outside of the device, and you can't see them, but there are also vias directly under the device. So these vias are helping to take the heat from the top layer of the board and spread it down to the buried layers, which are not illustrated here, which can then further help to spread out the heat as well as to convect the heat off of the backside of the board. So getting those vias near to the device has much more effect than, for example, these scattered vias that are further away, because the heat has already been spread out by the time it gets to this point. And then this example down here illustrates using the chassis, particularly if the chassis of the enclosure or a smaller chassis like a EMI shield, which is metal, can help to spread the heat from the device using what would be what is often called a gap filler material. So here's an example of a component which is attached down to the board. In this case, it's illustrating a mobile phone example. And we have the metal shield over the device, and the recommendation which was implemented was to take a gap filler material, and this could be a grease, this could be a epoxy material, this could be a compressible thermal pad that connects from the component to this metal shield, giving a much, much lower thermal resistance than that air gap. Air gaps tend to have a very poor thermal resistance. And now there's a pretty reasonable thermal path from the device up into this metal shield. And this metal shield, which was already there, or this could be the chassis for the enclosure, which was already there for mechanical reasons or for electrical reasons, is now providing a significant thermal benefit at very little added cost or complexity. You can read through some of these other examples. Some of these should be pretty self-explanatory, but if you have any questions, feel free to contact anyone at TI and we can help you talk through how to improve the thermal design of any specific system that you're looking at. So, in summary, in this last section of our four-part series, PCB layout and stack-up are very important for thermal performance and must be considered. Devices, components which are dissipating heat, are strongly affected by the other devices that are in close proximity to them, which are also dissipating heat and must be considered. And there are many techniques, design practices, tools, resources available to help in the design stage as well as the optimization stage to improve the thermal performance of a PCB in a system in order to provide the best possible thermal performance for the component of interest and for the system of interest. So I hope this four-part series has helped you in your understanding and giving you some practical tools. Congratulations if you made it this far. If you have further questions, you can go to www.ti.com and search for specific products or search for terms like thermal, or feel free to contact me directly at romig@ti.com. Thank you very much.